We have shown that if we have the limit as x goes to a of the quotient of two functions, f and g, we've shown that if both of these functions evaluated at a give us 0, so if we have a 0 over 0 situation, we can evaluate this limit using L'Hopital's rule, which states that we can differentiate the top and the bottom. But what happens if instead of the top and bottom going to 0, if they go to infinity instead? So this time we have the limit as x goes to a of the quotient of two functions, f and g, but this time as x goes to a, f of x and g of x go to infinity. So let's take a look at this. I'm going to pick a variable, L, and I'm going to assign this to be the limit as x goes to a. We have f of x over g of x. We have infinity over infinity. I don't know how to deal with infinity over infinity, but I do know how to deal with 0 over 0. So I'm just going to rewrite this a little bit. I'm going to write this as 1 over g of x over 1 over f of x, like this. This is still the same as the original. If you work this out, you will get f of x over g of x. And as x goes to a, we know g of x and f of x are approaching infinity. So we basically have 1 over infinity, which is 0, on the top, and the bottom. And we know how to deal with 0 over 0. We can differentiate the top and the bottom. But that looks bad, so let me write it again. Alright, so we have L being equal to the limit as x goes to a. Let's do this carefully. So we have g of x, 1 over g of x. I'm going to write that as g of x to the negative 1 power, and I'm going to do the same on the bottom. So we have g of x to the negative 1 power, and we have f of x to the negative 1 power, and we're differentiating this whole thing. Alright, so we're going to use the power rule. So we're going to first bring this negative 1 to the front, and then we'll keep the inside the same, which is the g of x. And then we will subtract 1 from the power. We'll get negative 2, and then we will use the chain rule, multiply by the derivative of the inside function. Derivative of g of x is g prime of x. In the denominator, we basically have the same thing, but with f instead. So we're going to have a negative f of x raised to the negative 2 power times f prime of x. And first thing I'm going to do is cancel out the negatives. And now I'm going to rewrite this a little bit. So we have L equal to this limit as x goes to a. I'm going to break this limit apart. We have the limit of this times this. So I'm going to break that into the product of two limits. So I'm going to say that this is the limit as x goes to a. The first part here, we have g of x to the negative 2 power. Well, that's the same thing as g squared of x in the denominator. And when we have f of x raised to the negative 2 power, I can bring that up to the numerator, and it will become f to the positive 2 of x. And then we will still multiply by this part right here. So we'll say we'll multiply by the limit as x goes to a of g prime of x over f prime of x. Well, what is this right here? We have a fraction, and we have the numerator and the denominator both being squared. So what I can do is write that as the square of the entire fraction. So instead of writing it like this, I'm going to write it like this. And when we have the limit of something squared, it doesn't matter whether we square it first or take the limit first. So I can bring the limit inside of the square. So I can say that this is equal to this whole limit squared. Well, guess what? This limit right here, inside of the square, is exactly what we started with. It's our L. We assigned L to be the limit as x goes to a of f of x over g of x. So I can replace this right here with an L. So I'm going to say that L equals L squared times the limit as x goes to a of g prime of x over f prime of x. And now I'm going to divide both sides by L squared. So I'm going to divide by L squared, divide by L squared, cancel these out. So we have L over L squared, we have 1 over L equals the limit as x goes to a of g prime of x over f prime of x. And now I'm just going to do the reciprocal on both sides. So on this side we'll have L equals the limit, because when we're doing the reciprocal, it doesn't matter whether we take the reciprocal first or take the limit first. So I'm just going to take the reciprocal of this inside part right here. So we'll have the limit as x goes to a, and the reciprocal of this is f prime of x over g prime of x. And now we are done, because I can just replace L with our original limit, and we have shown what we wanted to show. So we know that L is equal to the limit, because this is what we defined L to be, the limit as x goes to a of f of x over g of x. So we've proved that this equals this, which is what we wanted to prove.